Hello YouTube. Today we're going to be working on sampling distributions. Pretty much what sampling distributions allow us to do. We obviously can't take an entire population and survey it in order to gather data. Why? Because it takes too much time. Things may change by the time you get all the data, and it's just irrational trying to get all that information. So what we do is you take a sample of the population with the goal of hoping that it best represents the entire population to make a statistical analysis on a given test or survey or whatever you're studying. So I kind of showed that in the pictures here. You might have a population that's like crazy with a graph that looks like this, but you take that small section and it might look like a standard normal curve. That's kind of what we want to hope for, so you can better analyze the data. So we're going to go into a really basic example that's just pretty much going to help you understand the process and where the mathematical concepts kind of come from and how they are used. So you have a simple example of a sample set with 7 digits or 7 numbers in it. So first thing you want to do, this is the entire population. So say this is the entire population of something. Say just like the population of something in a, I don't know, petri dish, or I don't know, something small. Trying to think of a good example. Like the digits of maybe each of those, maybe there's like 7 balls in a bag and each of them are labeled 0 through 6. Something like that, I don't know. But let's first take the mean of the entire population. Obviously there's the formula for it, but many of you know just to add all the digits up and divide by the total number, which is the population, and we get 3. So the average is 3. You could also just look at the center value as well. And this represents the mean of the entire population. So this is the average over the entire population. Now we take the standard deviation. Again, you could use the formula. You pretty much subtract the mean from each of the values, square it, add them all up, divide by n minus 1. The reason you do divide by n minus 1 is to make your sample less biased, or your statistical data, and then square root it in order to get the standard deviation, and you get 2.16. Okay, with that said, now say you have to give, want to choose 3 of those numbers of those 7 and see how many different possible combinations there are to choose 3 of those numbers at random. So this is the point when we start going into gathering samples. So you gather 3/7 of the sample and hope that it best represents the population. But how many possible outcomes are there? Well, if you use the formula for combinations is 7 factorial over 7 minus 3 factorial times 3 factorial, or you might know it as n factorial over n minus k factorial times k factorial, you would get 35. So I could take 3 of these numbers in 35 different ways. Now I'm actually going to write down all those possible combinations, so I'm going to list them in terms of 3 and all the 35 possible combinations for gathering those samples. So boom, here they are. So I just gathered 3 at a time in order. There are 35 there. And now what we're going to do is we're going to take the average of each of those samples. So the average of 0, 1, and 2 would be 1 for that first one. And I'm going to do that for every single one of the 35 terms. I'll do that in purple. So we have 1, 1.3, 1.7, etc. That's just the average of those 3 values. Again, you add them all up, divide by 3, add them all up, and divide by 3, just in each of the sets. Do that again for the second row and the third row. So now we have the individual means per sample gathered. Now what we want to do is get the mean of the sample, which is going to be represented by y bar. So if I take the average or the mean of the sample, if I add all those up, and they're how many total? 35, and you divide by 35, then you get the mean to be 3. Now notice how this mean of the mean of the sample, if that makes sense, is equal to the mean of the population. So yes, this is a good representation because the average of the population is 3 and the average of our sample is 3 as well. Now getting into this stuff later, you might not know the mean of the population, but you will hope that it's around the same mean here for the sample. So if you plot the relative frequency and the number of like the means we got, so these were all the mean values we got. You got 1 to 5 pretty much. So that's everything in purple over here. So those were all the means. of each sample set we took. Now, how many times did those occur? Well, that would be listed here. So the 1 only occurred once, the 5 only occurred once, but the 3 occurred 5 times. Now, if you notice, you can kind of see, is that normally distributed? Yeah, there's 2 1s on the top, 2 1s on the bottom, 1 or 2, 2, 3, 3, 4, 4, 4, 4, and then 5 at the top. So yes, this is obviously distributed normally. So if you plot that on the histogram, it doesn't really look too well the way I drew it, but you can see that it's relatively, curved. It has that mound shape. So now, real quick, there's going to be something we're going to be talking about here, sampling error, standard error. So it's just the standard deviation over the square root of the sample size. And we did that, that is the standard deviation of the set. So here are some things that we need to cover for the sampling distributions. Pretty much, if you want to see if your sampling distribution is valid compared to the population, you want to make sure first that the average of the sampling size is equal to the average of the population. Remember, pretty much if they have the same mean like they did over here, right here, where the 3 is equal to 3, that it's a good representation. So you also want to make sure that, we'll get into this sort of later, I'll talk about it, due to sake of time, so I'll kind of just touch on it. But the standard error, or the standard deviation of the sampling, of the mean of the sample is equal to the standard deviation over the square root of the sample size. Oops. And finally, we have, if y has a normal distribution, then y bar has a normal distribution. Now, pretty much, that's saying if there's a normal distribution with this set here, which there is, then the mean of the sample and the sample that you gather should also have that same normal distribution. So pretty much you're saying if the actual entire population has a normal distribution, then your sample should as well. Also, there's something called the central limit theorem, and this is really important and really cool as well. So it says if n is really large, then y bar is approximately normal. Now there's two things kind of wrong, not really wrong, but difficult to wrap your head around in terms of mathematics. Large and approximately, those are very ambiguous, and so pretty much, the large is determined by whoever's doing the study. I could say the large could be anything of a sample size 30 or greater. It have to be maybe 1,000 or greater. It depends on the context of which you are doing your study. And approximately normal is, how do you know what approximately is? Well, I was thinking that the central limit theorem would have to do with limits. So if n goes to infinity, your sample size gets increasingly large over time, then you are closer and closer to a normal distribution. That's what it's saying. So if you keep increasing the number of people you survey, or the number of, or the sample size of your population, you are bound to get closer to the normal distribution. Now, why would we want to do this? Is because we want to have this normal distribution. Statisticians love having that normal distribution. It makes data so much easier to analyze and understand. If you get really down to the basics and see if there really is a correlation, but that doesn't necessarily apply causation, but still, you can have that those tools at that toolkit available to you. So I hope this helped for you guys understanding sampling distributions and how they can be applied in stats. Thank you.